Good afternoon. Welcome to the Asian Pacific Analysis Seminar, Analysis and PD Seminar. This is Zhouping Xin from the Chinese University of Hong Kong. Today we are very happy to have a speaker, Professor Tao Luo from City University of Hong Kong. Before start of lecture, I say a few words on the speaker. Professor Tao Luo graduated from the Chinese Academy of Science in 1995. And he's an expert on hyperbolic conservation laws, fluid dynamics, and has done some very interesting work on interfacial dynamics. And he was a professor. He spent some time in University of Michigan, Ann Arbor, and Georgetown University before he joined City University of Hong Kong in 2016. And recently he's working on interfacial dynamics for both compressible and incompressible fluids. And today he's going to give a talk on estimates and geometry for free surface problem of fluids with heat conductivity. Okay, Tao, yeah, please.
Yeah, okay, yeah, I thank the organizers for the invitation and thank Zhouping for the kind introduction. So I'm very happy to give this talk here. And this talk is based on the joint work with Professor Hui Zhen at Tsinghua University in Beijing. Okay. And so today I'm going to talk about the estimates and the geometry for free surface problem of fluids with heat conductivity. So let me start with a free boundary problem of incompressible Euler equations. Okay, so the free boundary problem is like this. So the first equation is a Euler equation. So incompressible Euler equation because here is a divergence free, and here V is a velocity field. Okay, V is a V1 to V, and N is a space dimension. V is a velocity field, and the P is a pressure. And the G here is a gravity. Okay, so now on the boundary how so suppose we have a fluids and the boundary will move, but how does the boundary move? The boundary moves with fluids. That means normal velocity of the boundary. This means the normal velocity of the boundary equals to the normal component of the fluid velocity. So here V is the fluid velocity. Okay, and so this is how boundary moves. And on the boundary have pressure equals to 0. For example, if you model a incompressible liquid and the outside is the air, then take the air pressure is to be 0, then we will have this problem here. And here the unknowns is dt. dt is a fluid domain, and also the unknowns are this fluid domain dt, and also those fluids variables v and p. Okay, so here is the problem, and so the dt here is really the changing domain occupied by the fluid at time t, and here this v gamma t is a fluid boundary of the domain, and v of gamma t is the normal velocity of the boundary. Okay, and the n here is outer normal, unit normal. Okay, so that's a problem. So this free boundary problem is that you give a initial domain called the d0, and inside this initial domain, the initial velocity is given. So here is a formulation of free boundary problem of incompressible Euler equations. And the typical domain dt is there are the two cases. One is to model the Euler wave, but in that case, the dt is diffeomorphic to half space, lower half space in that case. And another case is to model the droplet. In that case, dt is for example, is a simply collected bounded domain. Okay. So here is the case. And for this free boundary problem, for example, for the water wave problem, so that means when we assume that the fluid is a rotation law, and in that case, the local wall pulseness was without consider the case without the surface tension. The local wall pulseness was first did by Shijue Wu in 1997 and 1999, yeah, for the local wall pulseness. And later on, she did the global wall pulseness too in 2009 and 2011, and also for the global things in the local and the other local and so forth. Okay, and also for this global solution for the rotational, of course, you assume the rotationality. So so in various settings, for example, with the surface tension, finite depth, so on and so forth, and are very active. So and, you see by those work here, and so just now I mentioned that the results for the case of a rotational flow. If without this assumption and the work for the local wall pulseness or a priori estimates done by the following four people, for example, Cristolo, Lindeberg, and Colin and Schkoller, and Shata, and then Pin Zhang and Zhifei Zhang, so on and so forth. And for the finite time singularity, for example, this kind of splash singularity was done by Cordoba, Fairfan, and those people. And just now we talk about the rotational flow. For example, for the problem with the vorticity, for example, the simplest case is with a point vortex by Xu, and also with a magnetic field, and it was found by Wang, Yanjing Wang, the Zhouping, that the magnetic fields has induced dissipation, yeah, leading to the global existence. Yeah. And so for the water wave problem, without for the incompressible Euler equation, in the case without surface tension, so there is the important stability condition called the Taylor-Sand condition. That means on the boundary, the normal derivative of a pressure is strictly negative. This plays an important role in the wall pulseness, okay, without surface tension. So let's look at this condition. For example, suppose dt is a boundary domain, okay, the boundary domain, and simply collect it, and for example, for the rotational flow, that means the vorticity is 0. Then if we take let's see, take the divergence of a momentum equation, we get this initial problem for the pressure. So in that case, if it's a rotational, that means divj equals djvi, then you have a sign here. So that means the Laplacian p is negative, and p is on the boundary is 0. Therefore, the strong maximum principle implies this Taylor-Sand condition. This is for the rotational flow. Actually, for the water wave problem, this Taylor-Sand condition was proved by Wu. But for the problem with vorticity, this is the assumption. Yeah. So here is so just now I talked about the results about the incompressible Euler equation, and for the incompressible Navier-Stokes, for example, actually the local results and the global wall pulseness was under long-term behavior was done by, for example, Tom Bell, Engel, and Tice, and those people. And for the vanishing viscosity, because here I mainly talk about the invasive flow. Therefore, so I want to emphasize the traction between the Navier-Stokes and Euler. Then in that case, there is a vanishing viscosity limit. For example, for the incompressible Navier-Stokes, it was done by Masrudi and Rosset, and for also by Yanjing and Zhouping on the both when both vorticity, both viscosity and the surface tension tend to 0 at the same time for the incompressible, and also by Zhouping and the other people on the compressible Navier-Stokes. Yeah. So here I'm talking about the problem. So this problem is for another fluid. It's so this system is in my understanding is in between the compressible and the incompressible fluids. But the emphasis is on the case with heat conductivity. So how does this system come? So here is the system we want to talk about. This models the heat conducting invasive flow. When the Mach number is small, that means it's highly subsonic. So how does this system come? So for example, we take the compressible Navier-Stokes equation, but without viscosity, but with heat conductivity, and then we take the Mach number 10 to 0, then this system can be derived. Actually, this equation is from the momentum equation, and here this is for this divergence V equals kappa times Laplacian of temperature T. This comes from in the compressible equation. You write the equation for P, then you will get this equation, the limit equation, and this is from the energy equation. Yeah. So here V is again is a velocity field, and P is a pressure, and the T is a temperature, and here, but this T, this kappa, the important thing is this kappa. This kappa is what? Is heat conductivity. Therefore, we look at this system here. If this kappa is 0, if a system without the heat conductivity, then we have a divergence V is 0. Then in that case, is reduced to the incompressible Euler equation. Or another case is when this temperature is constant, then we also have a divergence is 0. So in that case, it reduces to the homogeneous incompressible Euler equation. But generally speaking, when kappa is not 0, when the heat conductivity is not 0, so the fluid for this fluid is not incompressible anymore. And if we take a closer look at this equation, divergence V equals kappa Laplacian T. For example, in the one-dimensional case, that means so we can get the V minus kappa times gradient of T 0. That means, for example, in the one-dimensional case, that means the flow somehow is due to the fluid velocity is due to the gradient of temperature. So that's an interesting phenomena of this system. Yeah. So for this system, we also consider the free surface problem. Free surface problem, we consider problem in the physical dimensions. For example, physical dimension n is 2 or 3. So we get this problem. Yeah. So unknowns to be determined is the velocity field, the temperature, and the pressure, and the domain D here. So the problem is so at first we give simply collective bounded domain. This is the initial domain D0, and on this initial domain we give initial data. Initial data is fluid velocity and temperature of course, satisfy this compatibility condition. So, and we want to find this set D, space-time domain D, and also the vector field V and the scalar temperature T, and solving the problem, solving the equations, and satisfy the initial condition, okay, and the boundary condition. Boundary condition, that means as before, the boundary is so this means the boundary is moving with the fluid on the boundary. The pressure is 0. Actually, the pressure is any constant, because you add any constant to the pressure, it doesn't change the equation and the problem. On the boundary, the temperature is a positive constant. Of course, there is another boundary condition for T, but we consider that's a kind of a lobing boundary condition. And but here we consider this a initial boundary condition. That means you have a exterior. So now you have a fluid domain, but you have an exterior atmosphere. That means exterior. So exterior, the temperature is constant temperature, and the pressure is constant. So those are things we want to solve. This is the problem we want to solve here. So our goal is to prove the a priori bounds for this problem under the Taylor-San condition. So this is the initial Taylor-San condition. Yeah. So for this free boundary problem, so as I mentioned just now, there have been extensive study on the incompressible Euler equations, and so here I want to make a comparison of the problem for the incompressible Euler equation. The first thing is for the incompressible Euler equation, there is a basic energy principle. That means a conservation of kinetic energy given by this. And for the compressible isentropic Euler equation, the basic energy principle is here. It includes kinetic energy and those and also the internal energy, like this. Yeah. Those are basic energy principles in conservation of energies for the incompressible, for the problem of incompressible Euler equation, and also the compressible isentropic Euler equations. But those are energy principles are very important for in the study of those of the free boundary problems of those two equations. And then I think it's also important for other related free boundary problems, for example, for MHD. However, for our problem studied here, if we take the kinetic energy, we get this, right? It equals P times divergence V. We get this. Therefore, we don't have a conservation of energy anymore, and this involves first order derivative of V. Actually, so for the isentropic compressible Euler equation, P and the divergence V are related, but here for our problem they are not related. P is actually for our problem P is a non-local quantity. I'll address this issue later. And for the incompressible case, divergence is 0, therefore this is 0. But for our problem, we just don't have the conservation of energy, and actually we don't have an energy principle. So this is one issue. This issue contributes to the loss of one more derivative than the problems on the incompressible and the isentropic compressible Euler equations. This is the first issue. Another issue is about the regarding. For example, for the incompressible Euler equations, so this we have this diminisher problem, as I said just now. For this diminisher problem, this diminisher problem is crucial to build up the regularity. So roughly speaking, if the boundary is smooth, so in that case one. So for this problem is a one space derivative of v gives two derivative of p, and but again come back to the momentum equation dtv plus gradient p equals 0. So then v gain one time derivative. Okay, this is crucial in the study of regularity of free boundary problem of incompressible Euler equation. However, for our problem, of course, we can also have this diminisher problem. Here T is temperature. We have this is therefore this is elliptic operator of P. But on the right hand side, besides this term, we have one more term dt divergence v here. dt divergence v here, so it involves space-time derivative of v, and the dt divergence v actually is given by in terms of velocity and the temperature like this. And of course, on the boundary p is still 0. So therefore, there is one more term here. Okay, so so we also use this to build up regularity, but the problem is on the right hand side we have this dt divergence v. Here this dt is a material derivative. So we have this dt divergence v. Therefore, it involves a space-time derivative of velocity v. Therefore, this is one more reason for the loss of one more derivative. Actually, because here we have a dt divergence v, therefore it's crucial to understand the divergence v of the problem. Actually, the divergence we derive that divergence we satisfy this parabolic equation, but on the right hand side, this nonlinearity. Those are nonlinearities. For example, here you have temperature and also Laplacian of v. And here the coefficient here also there's a temperature here, but temperature is temperature also is determined by the divergence v, but it's determined by divergence v non-locally. Yeah. So here is inverse Laplacian. Inverse Laplacian is for the initial boundary condition. So here is how we get the equation of divergence v. I show you the equation of divergence v. So from those you can see. So we know that the problem is I mean, the coupling is much more complicated than the incompressible Euler equations. And also there is a problem for loss of regularity. Okay. So the main point of this free boundary problem, and also for the incompressible Euler equation is a coupling of boundary geometry and the interior solution. The coupling of a boundary geometry, actually in this problem, there are two quantities, two geometric quantities on the free surface is important. One is the second fundamental form. Another one is injectivity radius of normal exponential map. So the second fundamental form is nothing but the tangential derivative of unit normal. Okay, so n here, and here pi is the orthogonal projection to the tangent space of a boundary, and the pi here is for 0R tensor alpha. The tangential projection is defined like this. So just use this is a Euclidean metric. You subtract the normal part. Okay, this tangential. This is an orthogonal projection. And here is a projection formula. I'll come back to this point later. That's it. Another important geometric quantity on the boundary is the injectivity radius of a normal exponential map. Okay, it's it's given by this. It's denoted by utah 0. So this is the largest number such as this map, starting from the boundary, and to this starting from the boundary and the utah here. So that this map. So that means starting from boundary a point on the boundary along the normal direction. You make a map such that this map is the largest number utah 0, such that this map is an injection. So this called the injectivity radius. So injectivity radius here in the free boundary problem, the lower bound of this injectivity radius is important, because the lower bound of it is used to prevent the surface from self-intersecting. So the thing is to construct the higher order energy functional. So let's see. Let's go to this energy functional. Energy functional, of course, E0 is something like a kinetic energy, of course. But the problem is that this E0 is not conserved. So the higher order energy functional is given by this. Here T is the temperature. Here Q is a quadratic form, and here we use Einstein summation convention here. So here Q is what's Q here? But before we talk about Q, we look at this energy functional. There are two parts of this energy functional. One is interior part. I mean, not interior part include this three parts. The first part is here. The second part is a curve. Is a vorticity, the derivative of vorticity, and also the space-time derivative of divergence. Also, there is the boundary integral here. Boundary integral here is a boundary integral is like this. So the problem is that because the things that we want to understand, we want to estimate the evolution of this energy functional. So therefore, we take the time derivative of this energy functional, and then when we take the time derivative, then we use the equation with time derivative of velocity field. So it reduces to the space derivative. Space derivative. Therefore, there will be an integration by parts. By using the equation, you have space derivative of pressure. Therefore there you do the integration by parts. Integration by parts. Then we'll find a boundary term, but that boundary term cannot be controlled. But then therefore we introduce. Therefore this boundary integral is introduced such that the derivative of this boundary integral, the time derivative of this boundary integral, leading term cancels the leading term of the boundary term of the integration by obtained by using integration by parts, as I mentioned just now. Yeah, this is important consideration here. And but what's here dt is as I said is a material derivative. So so then what's this q here? What is quadratic? What is q here? This q is a quadratic form. So this quadratic form is given by this. This q is a positive definite quadratic form. That means q, for example, for two tensors alpha and beta. So on the boundary is an inner product just for the tangential components, because this is the tangential component of alpha. Pi alpha means the tangential component. But when you move to the interior of the domain, this co-alpha alpha is enclosed enclosed to the norm of the full norm of alpha square. So in the interior, okay. So here is for the quadratic form of Q, and the construction of Q is obtained by extending the normal unit normal on the boundary extended is to the interior to get a vector field. Yeah. So let me come back to that energy functional. Energy functional. So we got this. So if we look at the interior integral, so there is the important thing of this kind of thing due to the it's actually the Hodge type decomposition. So the Rth derivative of V, the L2 norm is L2 is bounded by this. But here you see there's a difference here. Here the integral is of R minus 1's space derivative of divergence V, but here we got the problem is different. Is about the time derivative of R minus 1 time derivative, then one spatial derivative. So it's different. Why? But you may ask me why don't you use this? Because when we use this, we cannot estimate the time evolution of this, because this is because of the equation satisfied by the divergence. So by the equation satisfied the divergence, it's natural. It's natural to consider this instead of this term. Yeah. But later on, after we get the those estimate, we can recover the estimate for this. Okay. So here is the result. So for the initial data set, we still here's the volume of initial domain. Here is a maximum value of a second fundamental form, and also the lower bound of injectivity radius of exponential map. And this epsilon 0 is for the Taylor-Sine condition. And also we assume the initial temperature has a lower positive bound and the upper bound. And we assume the first derivative of pressure, velocity, and the temperature are bounded, denoted by M0. So in that case, here is our main result. This joint work with Hui Zheng at Tsinghua University. So for the space dimension n equals 2 and 3, suppose those quantities are bounded, and also of course the initial energy up to the n plus 2 order energy are bounded. Then we can find the time. This time continuously depends on those initial data, such that in this time interval we have an estimate of total energy is bounded by the initial total energy, and also we have estimate of boundary geometry. That means the bound of a second fundamental form, and also the lower bound of injectivity radius is bounded by the initial geometry here. And also we have Taylor-Sine is preserved in this time interval. So that's our mean result. So here there is a issue. There are some issues I want to talk about. So for this problem, just now I talked about the loss of a derivative, and this, and also there's the issue on the estimate of the boundary geometry. For example, on the bound of segment of fundamental form, for the compressible for the incompressible Euler equation. So here theta is a segment of fundamental form. So this is a projection formula. This means d squared, the second derivative of pressure. So the tangential component of second derivative of pressure is given by this second fundamental form multiplied by the normal derivative of pressure. Because of the Taylor-Sine condition, this dnp is away from zero. Therefore, we can divide by this dnp both sides. Therefore, if we can get the upper bound, the bound, if we can get the bound of this L infinity bound of the second derivative of pressure, then we can get the L infinity bound of second fundamental form. This was stated. This was stated by Cristoro and Linda Brad, and actually by using this, actually in their paper for the incompressible Euler equation, so the L infinity bound on the boundary of the second derivative P is given by this. So here the K1 is another geometric quantity. So this is just from the Sobolev embedding, and from this Sobolev embedding, it can be bounded by this quantity. Here E0 is a kinetic energy, and the ER is given by this for the incompressible Euler equation, and the volume dt, because for the incompressible fluids, volume dt is constant. So therefore, d squared is bounded by this. However, for our case, when we will try to use this projection formula, we get the estimate of the second derivative pressure. I mean, the L infinity bound on the boundary of the second derivative is given by this. Given by this, because on the right hand side, it involves the second from the L infinity bound of the second derivative. Therefore, if we want to use this projection formula to bound the second derivative, this doesn't work, because on the right hand side it involves second derivative involves L infinity bound of the second fundamental form. Therefore, this method, this approach of using this projection formula to estimate the second fundamental L infinity bound of the second fundamental form doesn't work for our problem. So what can we do in that case? What can we do? So therefore, instead of using this projection formula, we use evolution equation for the second fundamental form. But when we use the evolution equation of a second fundamental form, we get this estimate. This is the derivative. The time derivative of dt theta is given by this. So therefore, if you look at the right hand side, therefore we are to estimate the L infinity bound of theta, we need to estimate the L infinity bound of the second derivative of velocity field. But the second derivative of velocity field doesn't appear in the equation. For the incompressible Euler equation, so the L infinity bound for the first derivative of velocity is enough. Is sufficient for the estimate. But here for our problem, we need to estimate the L infinity bound. L infinity bound of the second derivative of velocity field on the boundary. So this is another reason of losing one more derivative than the incompressible Euler equation. So that's another reason. And also it should be so let's take a closer look at this estimate. So in the equation only the first derivative of velocity appear in the equation, and there's a second derivative of velocity doesn't appear in the equation. Therefore, to estimate the L infinity bound of this second derivative of velocity field is quite involved. This another point I want to make. So the key point is here is let me come back to the energy functional. So the problem then is to prove that the time derivative of those energy functional, I mean ET, the time derivative of this energy functional is bounded by itself under some a priori assumptions. For example, a priori assumptions including the R infinity bound of first derivative of V, P and VP and T, and also it involves the bound for the theta second fundamental form, and also the lower bound of injectivity radius. Under those a priori assumptions, we can prove that the time derivative of this ET is bounded by itself. Then with this energy bound, we prove that those bound are in the a priori assumptions. One is about the boundary geometry, as I mentioned just now. Therefore, I think I'm done, and I stop here, and thank you very much for your attention and listening.
Okay, thank you, Tao. Thank you very much for the very nice lecture. And now it's time to for questions. So any questions from the audience? Yeah, if you have a question, you can unmute yourself, or you can send the question by chat.
You have a question, please raise the hand.
Yeah, raise your hand. That's right. Okay.
Oh, there is a question.
Zhouping,
Yeah.
Professor Makino has a question.
Okay.
May I ask you?
Sure.
Yeah. Very interesting talk. Thank you. But
Thank you.
Your domain is surrounded, wholly surrounded by a free surface.
Yeah.
How about some part of boundary is solid or fixed case? For example, your external force is gravitation.
Yeah. So here we don't consider the
you can assume some
You
rigid
mean
boundary.
self-gravitation? So that's the case for a star. So we're not considering that case. But I think for the local in time, if you add a self-gravitation, it will be a lower order term. Therefore, for the local in time, I think it can be done. But for the large time, that's another problem, because for the long time dynamics, the self-gravitation is a different story. But local in time, it should be okay.
Uh-huh.
Okay.
Yeah, but for the compressible fluids, for example, you have a self-gravitation, so that model the gaseous star. Then on the boundary, you have for gas. Then on the boundary, it should be for stars, gaseous star, the electron boundary would be a vacuum boundary. So in that case, we have degenerate equations. That's and the degenerate problem. That's a different story, I think.
I don't know. I imagine an incompressible stratified atmosphere on a flat Earth. How about that? In that case, the boundary is some xn equal 1, 0.
Yeah, so rho is 0. Yeah, in that case, so that's degenerate. That's different from this case.
So,
yeah, for example,
so the problem is different. Yeah.
Yeah, they're different because it's degenerate. Yeah.
Thank you.
Okay.
Yeah, but also people try to study the incompressible, the stuff incompressible fluids. Also, for example, Archimedes and Bill studied that problem, a stationary problem. Yeah, for the incompressible star. Yeah, so sometimes it also makes sense. I think a different depends on how star, what kind of material of the star. Yeah, I think.
Okay, Tao, there's another question from Professor Kurt Williams. So he asked that, could you explain the terms in the energy functional? I
Okay.
see the analytic terms associated with the vertical and the transport flows. Do the Q terms take care of the internal energy and the compressibility conditions?
Oh yeah.
Any physical interpretation of your energy functional?
Yeah, well, let's go back. So this one is a. Oh, yeah, let's go back. This one is really due to the Hodge decomposition to estimate the derivative, high order derivative velocity. Hodge decomposition, for the Hodge decomposition without the boundary, so it's a controlled. The L2 of dr is controlled by r-1 and the curve and the divergence, right? So this Hodge decomposition. Now this term, the starting point of the construction of this functional, right? Yeah, but for our problem, because this equation satisfies the divergence, therefore it's given by this. But see, this is from the mathematical point of view. But from the physical point of view, so the divergence measures the compressibility of the fluids, and it's a compressible part. And the curve, I mean, the vorticity is an incompressible part. I think it's something like that. And also there's the physical meaning of this. I mean, the last term is in my understanding, is a surface energy. It's something like the last term. Here is the surface integral. Yeah. somehow relate to the surface energy.
Okay.
Right? Yeah.
Okay. Yeah, I hope you answered the question from Professor Williams. And I think then you also have a question, right, Daniel?
Yes, I would like to know something about the long-time asymptotic behavior. So I mean,
Oh, that's a difficult question.
I understand because there can
Yeah,
many
for
things
here,
happen.
Yeah, with the vorticity,
Yeah,
even for the Cauchy problem without boundary, you don't know what's going on, right?
Hmm.
So I think that's a one thing. Another thing is that without for the rotational flow, unfortunately, this problem cannot be rotational. Yeah, because initially it's initially it's rotational. Later on, as time becomes a positive, it becomes you have a vorticity immediately. Therefore, it's the vorticity. So for the long-term dynamics, for this problem, I think it's really a very, very challenging problem because we don't know how to control the vorticity. This is just as for the incompressible Euler equation, even without the boundary for the Cauchy problem. So that's a challenging part.
But you mentioned at the beginning one condition for the global existence. So that the pressure points inwards, and so such kind of things could not. So that the boundary condition actually could it make better than the standard Euler equation maybe, and that therefore one could actually
it could be, but that global problem is only for the case of rotational flow, right?
I see. Okay.
But for this problem, no way to study the rotational flow. Yeah, but the hope is to find a kind of mechanism. For example, I don't know which kind of a mechanism, but the only hope the hope is to find a kind of mechanism such that we can control the vorticity, maybe. But I think it's going to be also another issue is that for this bounded domain, without for this bounded domain, because it's a bounded domain without the viscosity, you don't have any kind of dissipation mechanism. And for the water wave problem, it's on the unbounded domain. Therefore, it's a kind of dispersive effect. Okay, dispersive effect on the unbounded domain to have a decay of the solution. But here, for this problem on a bounded domain without a dissipation, so how to find the decay mechanism is really a hard problem. I guess this problem, for this problem in general, I think it will form a singularity in a finite time, I think, most likely. But I don't know how to prove it.
Thank you.
Okay, yeah, thank you.
So you mean even for small data?
Yeah,
that will be singularities.
I guess.
So the heat conduction you think is not enough. Do not give you some long-time estimate of solutions.
Yeah, heat conduction as for example, as I said at the beginning, because here we don't have any kind of energy principle.
Yeah.
So you don't have an energy dissipation, and the heat conductivity. For example, the simplest case, even we have a heat conductivity, we take the special case, very special case, that temperature is a constant. It reduces to the incompressible Euler equation, and for that we don't know for the bounded domain what's going on. Yeah, but I guess it should be a kind of formation of a singularity, even for the small data.
Okay.
So of course the hope that it's a very interesting question to study the lifespan. I mean, the lower bound and the upper bound of lifespan will be I think it would be a very interesting problem.
Okay. So in your talk,
The trivial lifespan is the 1 over epsilon, I think, because the local existence gives that automatically. But for something beyond that would be, I think, very challenging.
so one more question. In your talk, you mentioned and the way you estimate the second fundamental form.
Yeah.
By derived equation for that.
Yeah.
So that play a very important role in your analysis. So
yeah.
My question is, in that estimate of the the second fundamental form, does the estimate depends on the heat conduction coefficients?
They are coupled to each other. For this equation, it doesn't depend on that.
I see.
Yeah, but later on, when we estimate the second derivative of this, it relates to that. For this equation, yeah, it's really we don't use a fluid equation for this. Just use the condition that the boundary is moving with a v.
With the v. Okay.
Yeah, so that's we use that to derive this tensor equation for this evolution equation for theta.
Okay.
Yeah, we don't use a fluid equation.
Okay. Are there any more comments from the audience? So if not, let's thank Tao again for the very interesting talk.
Yeah, thank you, all of you.
Daniel, so that's I turn back to you, right?
Okay, thank you. No, that's okay. You can close the session. Everybody received an invitation email to a coffee break. Please feel free to join. It would be nice to have an informal chat with the speaker if he is available as well. And yeah, please join.
Okay. Okay. See you guys in the coffee break. Yeah.
Yeah. Okay.
Bye. Bye. Thank you.
Bye. Thank you.
Thank you.